Welcome back, exploring the arts and sciences, folks. Now that we're getting back into the groove of things, I want to remind us where we've been. Because remember, in just 6 weeks in INDS 100 so far, we've started back 5,000 years ago talking about cuneiform and hieroglyphs, and we've moved all the way through Mayan mathematics during that time. But importantly, this hasn't been done completely haphazardly. There's been a structure to this. Remember, moving through these different time periods and these different disciplines has been done to teach us something about the full breadth of the liberal arts offerings we've got here at SUNY Potsdam. And to do that, we wanted to start off by putting a liberal arts education in the context of different types of educations we could receive. And then when we moved into focusing on the liberal arts at SUNY Potsdam in particular, we talked about the fact that there are multiple different schools here, and these different schools focus on different types of disciplines, and each of these different types of disciplines ultimately has many different disciplines underneath them. So the structure to this course hasn't just been about different disciplines. Remember, the structure has also been temporal and geographic. So we started off in the ancient humanities in Africa, Asia, and Europe, and then we moved to the medieval period to talk about the STEM disciplines in the Americas and in the Middle East. And now we're focusing on the medieval Americas and STEM disciplines therein. So remember, when we're talking about civilizations indigenous to the Americas, there are at least 4 different regions we need to talk about. We could talk about North America, we could talk about Mesoamerica, or we could talk about 2 different areas in South America, civilizations that grew around the Andes Mountains region, and civilizations which grew around the Amazon River basin. And when we heard from Professors Medor and Miller, we were focusing on Mesoamerica around the Yucatan Peninsula here. In particular, we looked at the Olmec, we looked at the Maya, and we looked at the empire built around the Mexica, commonly referred to today as the Aztecs, which we see here. Before we get into Mayan mathematics, we should remind ourselves about the culture of the Maya more generally. Remember, Mayan civilization stretches back 4 millennia, and to avoid problematic indigenous erasure, we need to remember that there are millions of people of Mayan descent alive today. The classic period of the Maya, the golden age of the Maya, occurred from roughly 200 to 900. And during this time, the civilization of the Maya was composed of different city-states, some of which reached populations of 200,000 or so. And even though we'll be focusing on mathematical achievements of the Mayan culture flourished generally at this time, with a system of glyph writing, many different systems for keeping track of time, which were aided by impressively accurate astronomical work. And there's also a great deal of monumental architecture which was created during this time, including large ball courts and pyramids. As we move into Mayan mathematics, it's important to specify that we're going to be talking about Mayan arithmetic. So remember from a couple days ago, arithmetic is the theory of numbers. So as we start to move into Mayan mathematics, we need to start off by looking at Mayan numerals. And one of the things that the nerd in me is completely obsessed with is that the Maya created a numeral system which could represent literally infinitely many different numbers with just 3 symbols. And the first of those is the dot. The dot stands for 1. So 2 gets 2 dots, 3 gets 3 dots, 4 gets 4 dots. But then we introduce the second symbol of the Mayan numeral system, the bar, which stands for 5. Then we have 6, 7, 8, 9, and 10. Now you might be saying, we've looked at 10 numbers. 10 numbers are the base of what we do in mathematics, yet you only showed me 2 symbols. I thought you said there was a third. Ah, that's because the Mayan numeral system is a base 20 system, not a base 10 system. So we need to continue to 11 through 20 to see all of these different symbols. So continuing on, 2 bars and a dot gives us 11, 12, 13, 14, 15, 16, 17, 18, and 19. And it's when we move to 20 that we see our third symbol, the shell here, which stands for 0. So the dot and the shell give us 20 because we have a base 20 system. So there is a 1 in the 20s place and a 0 in the 1s place, giving us a total of 20. Now, we want to try to put this particular numeral system to work here. So let's say we start off with a Mayan numeral that looks like this, and we want to figure out what Hindu Arabic numeral this ultimately represents. In order to do that, we have to line up each one of these Mayan numerals with the particular place that it is in. So here, the very bottom is the 1s place. The next place up is the 20s place. Remember, this is a base 20 system. That means the next place up is going to be the 400s place, 20 times 20. So here we have 18 in the 400s place, which gives us 7,200. We have 3 in the 20s place, which gives us 60. And we have 0 in the 1s place, which gives us 0. Adding those all up together, we get the number 7,260. So if we start with a particular Mayan numeral and want to figure out what the Hindu Arabic numeral associated with it is, then what we do is we line up the place values next to each Mayan numeral, and we multiply that Mayan numeral times the value of the particular place that we find that numeral in, and then we add each one of those together. So that's how we get from a Mayan numeral to a Hindu Arabic numeral. The question is, what do we do to go in the other direction? If we start with a Hindu Arabic numeral and we want to end with a Mayan numeral, then we just need to, in a certain sense, reverse the process. To get from a Mayan numeral to a Hindu Arabic numeral, we multiplied and added. Now to go in the other direction, we're going to divide and subtract. So let's say we started off with the Hindu Arabic numeral 3,619, and we wanted to represent that as a Mayan numeral. As you see here, this process to do so looks a little bit like long division, but really it's an instance of what's called a greedy algorithm. And it's called a greedy algorithm because at each step, we ultimately try to take as much as we can and then deal with what's left over at later steps. So we want to start off here with the place value in the Mayan numeral system, which is closest to our number but doesn't go over. So the highest place value we're going to be concerned with is the 400s place. If we went further, it would be the 8,000s place, and that's higher than our number. So again, we want to start off by sort of dividing here, and we ask ourselves, how many times does 400 go into 3,619 without going over? And the answer to that is 9. And 9 times 400 gives us 3,600. So we take our initial number, 3,619, subtract 3,600 from it, and we end up with 19. So we need to, at the next steps, figure out how to get 19. So the next place down is the 20s place. And we ask ourselves, how many times does 20 go into 19? And the answer there is 0. So we've still got 19 left over. We move to our next place, the 1s place. And how many times does 1 go into 19? Well, 19 times. So the number 3,619 is going to be made up of 9 400s, 0 20s, and 19 ones. So that means the number 3,619 as a Mayan numeral looks like this one on the right here. Now, if you're worried that that was difficult to follow, you can rewind. Or if you want some more practice, this next slide here gives general procedures, general algorithms. You may have noticed I've used that word a couple times now. We'll talk about that in more detail next week. But again, this next slide gives general procedures for how to do this. So please feel free to pause on it. So again, if you're going from a Mayan numeral to a Hindu-Arabic numeral, this is largely about multiplication and addition. And if you're going from a Hindu-Arabic numeral to a Mayan numeral, this is largely about division and subtraction. Now, you might be wondering why I wanted to focus on some Mayan mathematics, and there are multiple different reasons here. For starters, I think it's really important for us to fight against the general Eurocentric trend we find in Western society, but Western academia in particular. But second, I think there's lots of interesting things we learn by comparing and contrasting the Hindu-Arabic numeral system and the Mayan numeral system. This can teach us really interesting things about mathematics generally. So, arguably, the most important similarity between the Hindu-Arabic numeral system and the Mayan numeral system is that they're both positional. They're both place value systems. And what makes something a positional system is that the number that a symbol stands for is partially determined by where the symbol shows up in the numeral. The easiest way to show something about positional numeral systems is by comparing a positional with a non-positional system. So here we've got the Roman numeral for 3, I. In each place the I shows up in that Roman numeral, the I stands for 1. No matter what position, no matter what place it is in, it stands for 1. This is to be contrasted with a positional numeral system like the Hindu-Arabic system, which we can see by looking at the Hindu-Arabic numeral representation of the number 333. Here, even though we've got the same symbol repeated 3 times, the first time the numeral 3 shows up, it stands for 300, a completely different number than it stands for the second time it shows up, where it stands for 30, which is a completely different number than the one it stands for the third time it shows up, namely 3. We'll get a chance to talk about this more next week, but having a positional numeral system gives us infinitely more mathematical capacities. So despite the fact that we have these 2 positional numeral systems here, they're different from one another in the fact that they have different bases. So again, the base of a positional system is the number which different places in a numeral are powers of. Taking the Hindu-Arabic numeral system, it's a base 10 system, because we start with the ones place, 10 to the power of 0, move on to the tens place, 10 to the 1, move to the hundreds place, 10 to the power of 2, etc. Whereas the Mayan numeral system is a base 20 system, because we start at the ones place, 20 to the 0 power, move to the 20s place, 20 to the first power, move to the 400s place, 20 to the second power, and so on. There's even a further difference between the two that we can get by building off of this first difference. Another facet of positional systems is the radix of the system. The radix of a positional system is the number of unique symbols in that system. And given that the base of the Hindu-Arabic numeral system is 10, and the radix is also 10, this makes it so oftentimes mathematicians interchange the base of a numeral system with the radix of that system. That is, we unfortunately hastily generalize from the system we're most used to, but what the Mayan system shows is that the base and the radix of a numeral system need not be the same. Despite the fact that the Mayan system is base 20, the radix is only 3. There are only 3 symbols in the Mayan numeral system. The shell standing for 0, the dot for 1, the bar for 5. We can also see similarities and differences, as well as learn interesting things about mathematics more generally, when we ask why the Maya might have used a base of 20. It's commonly thought that this has to do with the importance of the whole human person to the Maya, which human persons standardly have 20 fingers and toes bordering the edges of their whole body, and this importance of 20 is continued elsewhere in Mayan culture, where keeping track of time was extremely important. There were multiple systems that the Maya had for keeping track of time. 2 of these were calendars, one a 365-day calendar broken into 18 months of 20 days, with 5 nameless days, and another a 260-day calendar which consisted of 20 day names combined with 13-day numbers. All of this is important because these sophisticated systems for keeping track of time were connected to both astronomical work done by the Maya, which was the most sophisticated of anywhere in the world for centuries, and their interest in keeping track of time for religious rituals. And this is something which I think is greatly important. All too often, people think that mathematics, science, and religion don't go together. But the Maya show us otherwise, and we'll see when we continue into the Islamic Golden Age next week the same thing. Now, if you've been paying attention to these videos, I hope you know what's coming next. We've been listening to music at the end of all these videos, and today's gonna be no different.
This is original, Balama. Para la sagrada milpa. Hey, yo. Alabar a la milpa, símbolo de la fuerza, armoniza nuestro ser con la naturaleza que empieza y progresa, el retorno a la nobleza. Comienza en la columna, termina en la cabeza. Numalaj, Ajakamon, Pika, Chagüe, Justino, el Capiz. Kasetet, Numalaj, Agüen, Kapasem, Katik, Bali, Ule, Patak, Saeka, Ule. Hakale hakka katsini topetali maki kaki hirumat ni malak sakde blanco y celeste sakde camino al horizonte sakde como gato de monte sakde linajes desde siempre